This is an overview and demonstration of the progress made on my relay computer up to April 2018. Effectively, it's an updated version of the overview I did back in April 2016, so between that video and this, you can see what's happened in the last 2 years. Now, if this is the first you've ever heard of my relay computer, then please visit my blog at relaycomputer.co.uk, where there's plenty more information about this computer. So, here's the graphic I used in my last update video, which basically shows what progress has been made up to that point. The bits that were completed are shown in green, and the bits that I haven't yet started are shown in red. On the left-hand side is a diagram of the computer's architecture. This is covered in more detail on my blog, but effectively it shows registers A, B, C and D, along with the instruction register, ALU and condition registers are all complete. As you can see, there was many registers outstanding and we were without memory, program counter or incrementer. The diagram at the upper right shows the completion status of the physical card in each of the 4 bays W, X, Y and Z. As was, all 5 cards in the Z bay were complete, specifically the AD register, BC register and the 3 cards that make up the ALU, control, arithmetic and logic. There was 1 card complete in the X bay, the instruction register, and finally we had 5 partially complete cards in the W bay, shown here in orange, made up of the decoder card and then the controller and sequencer card pairs. Last at the bottom right is a list of the completed instruction classes, and as was, there's 3 instruction classes implemented, ALU, SETAB and MOV-8. So then, what's happened in the last 2 years? Let's update the diagram. Well, there's quite a bit more green than before, showing that the program counter, incrementer and memory units have all been completed. And these were the units that would take the computer from running one manually inputted instruction at a time to a computer that is more worthy of the title. With these 3 units, it will now be possible to enter a program into memory and then let the computer trot through that list of instructions without any further intervention needed from the user. Card-wise, there's 3 new ones in Bay X and 2 in Bay Y. Just as with the sequencer and controller, the memory and incrementer are implemented using 2 cards each. Speaking of the controller and sequencer, they've had further bits added to them to handle moving on to the next instruction in memory. But as they're still a way off being fully functionally complete, they stay as orange. Finally, at the bottom right of the diagram, we see there's no changes to the instruction classes, but I'll start implementing more of these in the future, and the key one is going to be the goto, which will allow branching in programs, and that's where the computer starts getting really useful and capable of running more complex programs. Okay, so with the progress diagram out of the way, let's have a quick overview of the computer as it currently stands. So, welcome again to my relay computer. This is a picture taken face on, and I've finally taken the plunge and invested in some photography kit, lights, backdrop, that sort of thing. Of course though, that's no guarantee that I'll know how to use the new kit properly, but hopefully these pictures are an improvement on last time. One thing I've definitely scuppered myself with is choosing supremely glossy panels for the computer that reflect everything. So once again, you can see the camera tripod and my knees clearly reflected in the lower half of the computer. Oh well, I'll get the hang of this photography thing one day. Anyhow, if I rotate the computer clockwise, here's the view from the right, back and left. And yep, there's still some cables hanging out the back, but these will eventually join their siblings and be neatly routed within the case. Speaking of which, you probably guessed that the case is a half-finished job, and mainly that's to ease working on the insides for now, but eventually it will be completely encased in back perspex, so it'll look a little bit like this. Both the front and rear covers are removable, and with them removed, this is what it looks like. If we take a closer look now at the front and rear, you can see that the enclosure is broadly split into 2 halves. The upper and lower enclosure. Focusing on the upper enclosure for a moment, we can see that it's broken into 3 sections. At the bottom are the primary switches, which is the main way that the computer is operated. These are accessible even when the front door is on the computer. At the top left, when viewed from the front, is display A. This shows which control lines are currently being operated by the computer, but also allows the user to directly operate those control lines for debugging and testing purposes. Alongside this is display B, which shows things like the status of condition registers, current instruction code and class, ALU operation, data and address bus values, and finally the amount of juice the computer is consuming. Here's a close-up of the upper enclosure. And here's it seen from behind. There's actually less to see here than in my last update video, as there's a whacking great power supply stuck in the way. Although visually obtrusive, this does now of course mean that the computer can run under its own steam, as it were. The lower enclosure is split into 4 bays which take 5 cards each. Viewed from the front and going clockwise, the bays are named W, X, Y and Z. The cards are designed such that any Z card could fit anywhere in the Z bay, but a Z card couldn't be used in the Y bay. This is because each bay has unique connectors for each of the card types. Let's take a closer look now at each of those bays, and I'll go in alphabetical order, starting with bay W. First up is a sequencer, which is spread across 2 cards due to the number of relays and connections required. The diagram on the right shows what each of the card's LEDs actually mean. Note that the grey dots signify where future LEDs will be placed as the card gains more functionality. For now though, we can see the 9 states of the FSM on the left and the derived sequencer pulses A through to E on the right. Next is the controller, again made up of 2 cards, and finally the decoder at the bottom as a single card. The decoder takes the current value in the instruction register and decides which instruction class that represents. The controller then takes that instruction class and operates the right control lines at the right time according to the sequencer pulses. Moving on to the next bay, bay X, we find the instruction register, incrementer and program counter. For some reason, I haven't got around to printing off a legend strip for the incrementer and program counter, but have gone to the trouble of 3D printing the plastic strip on which the legend strip is mounted to. As it happens, I only got into 3D printing because I couldn't find a card legend strip holder thingy off the shelf. Much expense later and a house full of molten plastic, and here they are. The next bay is bay Y. So far, there's just a memory unit in here, which is another one that's spread over 2 cards. Now you might have noticed that this card bay is a bit brighter than the previous 2, and that's because it's missing the backplane which connects all the Y cards together. As it stands, the memory card has the buses directly plugged into it, but soon, as another card has come into this bay, I'll need to construct the Y backplane. Incidentally, I'm not going into too much detail on each of these cards, as you're probably fairly bored already, and needless to say you can find out more info at my blog. Yes, I will keep on plugging it. Finally, we arrive at the last bay, bay Z. This is the one and only bay that has a full set of fully completed cards. The first 2 implement the registers A, B, C and D. Again, for some reason, I haven't printed out a legend strip for those cards, but have gone to the trouble of melting PLA into a useful form. The 3 remaining cards make up the ALU, control, arithmetic and logic. Again, if you want a bit more detail on these, you know where to look. URL in the video description below. Please, thanks. Right, so that's pretty much it for the overview. Let's move on to actually getting the computer to do something interesting. And that's probably a relative term, but being as you're currently watching a video about a guy who's made a computer from relays, I assume that I'm in good company. Now, being as instruction-wise the computer is pretty much the same as it was in my 2016 update video, this section of the video is pretty much identical too. If you've seen this bit before, then feel free to jump to the demonstration section, and I'll put some timeline links in the video description to help you jump around this video, should you wish to do so. So basically, this is the same demonstration program I've used in previous videos. Hopefully this will be one of the last times I trot it out, and as I add more instruction classes to the computer, I'll be able to demonstrate something with a bit more flair. For now though, I'll stick with this one, as it does at least show using all of the instruction classes currently available to us. The main difference this time is that whereas in my last update video I had to manually load and run each instruction in turn, This time I'll be loading the whole lot into memory and letting the computer get on with running it, just like a proper grown-up computer. If somehow you've not seen this example program before, it's just a simple arithmetic sequence adding 2 and 4 together, then adding 1, multiplying by 3, and then finally subtracting 3. The result we're looking for, of course, is 18. First job then is to add 2 and 4 together to get 6. Now this program is written in assembly style mnemonics that I specifically chose for programming this computer. Now of course, this will all mean nothing to the computer, which is expecting a list of 8-bit instruction codes. And I'll take us through the process that takes this human-readable version of the program and converts it into something the computer can use. Taking a look at the architecture diagram at the right, we know that the ALU handles arithmetic operations amongst other things, and that it takes its inputs from registers B and C. Therefore, we want to get 2 into register B and 4 into register C. We could of course do it the other way around, with 4 in B and 2 in C. The ALU wouldn't care either way, and the result would be just the same. Getting 2 into register B is easy enough using the load immediate LDI command. So that's the first line of our program. Now for the programmers out there, you might find that parameter order a little bit odd. An LDI 2, B might make more sense, but my choice here is pretty consistent with other assembly languages, and you'll see all the assembly mnemonics I use here are consistent with each other also. So what about the C register? Can we do the same and LDI 4 into register C? Well, no we can't. The computer can only load a value into register A or B, so we'll have to be slightly more creative. Our only option is to load 4 into register A, meaning that at this point B holds a 2 and A holds a value of 4. We now need to copy the value in register A over to register C. Well, that's fine, as the computer can copy values between the A, B, C and D registers, and the command for that is MOV, which has a mnemonic of MOV, MOV. Yes, you heard me correct. The command to copy a value is called MOV. Now that's no doubt confusing if you've not come across it before, but don't worry, I'm not being contrary here. This is again consistent with quite a few other assembly languages, which also copy when you say move. Anyhow, issuing a MOV C, A will copy the value in register A over to register C. With the copy done, we now have all the right values in all the right registers. That is, B holds 2 and C holds 4. To add those together, we now get the ALU in on the action by issuing the add command. So where does the result of that addition go to? Well, the ALU can either load the A or the D register, and if we don't specify which, it'll assume it's the A register we want loaded. So once the add is complete, we'll have a value of 6 in the A register, which overwrites the 2 it held before. Also worth noting is that when the ALU does an operation, it also updates those condition registers. In this case, all 3 will be cleared, as our value of 6 is not equal to 0, would not have caused a carry, and doesn't have the sign bit set. Moving on, we now want to add 1 to the 6 we've got so far. Now we could load a value of 1, move things around, and then add 6 and 1 together, but the ALU gives us a much quicker way. If we copy the 6 from register A to B, we can then invoke the ALU increments command, which takes a value in B and increments it by 1. As before, we haven't specified a destination register for the inc operation, so the ALU will assume register A. And once the increment is complete, we'll therefore have a value of 7 in register A. As before with the add operation, the condition registers will be updated again, but leaving all 3 in the clear state. We now need to multiply the 7 held in register A by 3. However, this computer's ALU doesn't have a multiply function, so we'll have to do a bit of legwork ourselves. The trade-off here is a computer that's simpler to build, but at the expense of being slightly more complicated to program. Interestingly, once branching is implemented, we can make a little subroutine of commonly used functionality. So in this case, we'll make a reusable multiply function that we can call elsewhere in the program. For now though, we'll have to code it in place. So what is multiplication? Well, broken down, it's just repeated addition. So let's do just that. We can load registers B and C using the 7 held in register A, and then we add together back into register A. We now copy the value in A over to B and repeat. If you wanted to multiply further, we could just keep repeating this last action. Now, a clever way of doing this, more generically, is to loop around that last action as many times as needed. But we need branching for that, so that's one for the future. Anyhow, we end up with a value of 21 in register A, so we're nearly there. Last step then is to take the 3 from the 21 to get a result of 18. And we hit another blocker, as the ALU doesn't do subtraction either. Clearly, it's a fussy little calculator. So we need to get creative again. We can achieve the same effect by adding a negative number. So what's a negative number? No, that's not a trick question. It's quite obvious when we're using the decimal system, but bear in mind all the numbers we're using relate to an 8-bit binary value. Now, to represent negative numbers, we can pull off a trick known as 2's complement, where given a positive number, we can invert all the bits and then increment by 1. Now, the beauty of this approach is that you can tell you've got a negative number when the most significant bit is set. The other bonus is if you have a value of -1, which is 1, 1, 1, 1, 1, 1, 1, 1 in binary, and increment it, you get a value of 0 as you'd expect. Also, if you perform the 2's complement twice, you get back your original number. The trade-off here is that because you're using that most significant bit for the sign, you're reducing the range of numbers that you can represent. Bear in mind though that the computer itself has no idea we're extrapolating this meaning from the 8-bit value that it's adding. It just adds binary numbers together and that's that. So let's get -3 into register B ready for the addition. We start with loading 3 into register B and then call the ALU not operation to invert all the bits. Note that we're specifically sending the result to register D this time, as we don't want to overwrite the 21 we've produced so far, which is quietly nestling there in register A. Interestingly, half the challenge of programming a computer like this is juggling your values between the registers. We now need to increment that value in register D to complete the 2's complement operation, and we do that by copying register D to B and then calling increment back into register D. Note that we'll be seeing the sign condition register set following both the not and the inc operations, as for both the most significant bit is set. As it turns out, we could have actually cheated here somewhat, as the LDI instruction can load negative values, but I thought it would be worth exploring the longer route. Let's finish off then by copying the 21 in register A over to B and the -3 in register D over to C, and with a final add operation we get 18 in register A and our program is complete. So, now this program is written, what do we want to do with it? Polite suggestions only, please. The assembly language I've used here aims to be human readable, yet tightly coupled to the functions of the computer. In fact, there's a one-to-one relationship between each mnemonic and its associated relay computer opcode. Therefore, I'll need to convert the program line by line in a process called assembling. Now I'm going to do this by hand here, but eventually I'll write a program that can do all the work for us. The first step is to decide which instruction class each mnemonic represents and what parameters that instruction needs to take. Each mnemonic maps to exactly one instruction class, although several mnemonics can map to the same class. We can start by picking out the SETAB class instructions, which also need the target register and the value to load into that register. For this program, that's all the LDI mnemonics. Next, we'll hit the MOV-8 instruction class, which wants the source and destination registers as parameters. There's a one-to-one relationship here between the MOV mnemonic and the MOV-8 instruction class. Finally then, are the ALU class instructions, which cover a wide range of mnemonics, but in each case the class wants the destination register along with the ALU operation to perform. Note that it's here where we're resolving that default destination functionality, as that's a feature of our assembly language, not something that the computer itself has built in. The computer will always need the exact operation required to be spelt out for it. With a list of instruction classes and parameters, we're halfway there. Unfortunately, the final step is the worst. We've now got to convert each of these instructions to an equivalent 8-bit opcode that the computer will understand. We'll start with the SETAB class again, and using the tree diagram on the left, we can see that SETAB class instructions always start with a 0, 1, followed by a destination bit of 0 for A and 1 for B. And then the remaining 5 bits represent the value in binary that we want to load. Effectively then, it's just a case of writing the opcode for the action you want the computer to take. We repeat the same process for the MOV-8 instruction class, again using its tree diagram, which shows that we need to start with a 00, then a 3-bit destination code, followed by a 3-bit source code. Finally, we encode the ALU class instructions, which all start with a 1000, followed by a destination bit of 0 for A and 1 for D, and finally a 3-bit function code for the ALU operation that we wish to perform. And there we go. Finally, I hear you cry. One program assembled into a list of binary opcodes, or machine code as it's otherwise known, all ready for the computer to churn through. So enough talk, let's fire up the computer, get this code loaded into the computer and set it off running. It's demonstration time. On the right, you can see the program we've just assembled ready to run. If you skipped straight to this part of the video, and blimey, who could blame you, what you see before you is the code to perform a simple arithmetic sequence of 2 plus 4 incremented by 1, multiplied by 3, and finally with 3 taken off of it to get a result of 18. This allows me to demonstrate the 3 instruction classes that the computer is capable of so far, which are SETAB, MOV-8 and ALU. In the left column are the binary opcodes which I'll be entering into the computer, followed by the equivalent assembly mnemonic, and finally at the end are any comments. So let's crack on and enter the program into the computer. I can do this using the primary switches, entering each opcode in turn, and with a flick of the deposit next switch, that opcode will go into memory and the program counter is advanced by 1 step. Repeat AVU and you've got a program in memory. I'll finish off by loading an opcode with all bits set, which confuses the sequencer into locking up and will stop the program running. Off we go. Good, okay, the program should now be in memory. But don't take my word for it. Let's reset the program counter and then we can use the examine next switch to step through the program. Each time I push the switch, the current opcode will appear in the instruction register and will be visible in display B here. Off we go. Right, okay, so we're ready to roll. I'll reset the program counter, prime the sequencer, and we're off. So there we go, program complete. And if I pull up the value in register A, you can see it's 18 as expected. So that's one relay computer working as expected. Now okay, it's limited what you can do with it, but as time goes on it will gain more and more functionality. For now though, something that always seems to go down well is upping the clock speed, so let's run the program through at increasing clock speeds. And just in case you're curious, this is what it sounds like with the covers on. And that's pretty much it for this overview. As always, you can find more information at my blog, relaycomputer.co.uk, and there's also a simulator you can play with if you fancy at simulator.relaycomputer.co.uk. And finally, if you fancy having a go at writing your own program, there's a code editor at editor.relaycomputer.co.uk, which gives you syntax highlighting, other such fancy stuff, but doesn't save your code, so copy and paste anything you want to keep. Incidentally, I'm running a competition of sorts where I'll take 5 programs supplied by you dear viewers and run them through my computer and post the results back on YouTube. To be fair, I've not had any takers so far, so maybe it's a bad idea, or more likely the lack of branching is putting you all off, which is fair enough. But if you do fancy a go, take a look at my instruction set video linked in the description below, which has more details. Speaking of branching, that's where the relay computer is headed next. And although there's quite a bit of work to do to get there, needless to say I'll keep blogging and creating videos on here as I progress towards that next milestone. So all that remains is to thank you all for watching, and please do feel free to like, comment and subscribe, and I'll see you next time.